Let's look at the full RRS with CAE workflow to optimize a Francis turbine runner. Before the machine learning system can get to grips with optimizing a design, we need to establish a baseline sizing and component integration for the stage based on the most basic requirements of the turbine. That is, how much flow, how much head, and how fast will it spin. Plugging these numbers into TURBOdesign Pre, plus some other details about the working fluid, the inlet conditions, and how the stage should be configured, results in a complete 2D stage design for the runner and all the associated components if required. The volute, stay vanes, and guide vanes. Even at this early point, we have a realizable complete stage design that would meet the requirements of the basic duty specified. It may not be the most efficient or have performance at other operating points, but these extended performance requirements will come from the machine learning process, which we will set up. Here is the baseline design for the Francis turbine. With the given design specifications and the sizing created by TURBOdesign Pre with the 3D and meridial shape shown, we now need to establish the baseline performance in CFD across a number of operating points. The CFD domain is exported in step format for meshing. TURBOdesign 1 will automatically create a 3-domain configuration. The CFD analysis is set up using the CAE integration feature. We define the solver to use, target Y+, turbulence model and solver settings such as timescale factor, residual target, and the number of cores. In this case, 3 operating points with a fixed rotor speed and onset angle, at flow rates of 410, 450, and 500 kilograms per second, which simulate different power requirements from the grid. Note that we can specify a number of different output formats and domain configurations for the blade geometry, depending on what downstream analysis system we are intending to use. To integrate with Siemens Star CCM+, we use the step file format to create a solid which represents the fluid domain. Meshing, pre-processing, running the solver and post-processing are templated scripted processes triggered by a single run action, so we get consistency of analysis time after time. When we run the integrated CFD from inside TURBOdesign 1, we get back the solutions at each operating point. Total mesh size is about 228,000 cells for a single blade. Y+ remains below 5 for the wetted surfaces. So now the baseline characteristic is defined, and all the CFD results have been returned and organized within the TURBOdesign 1 environment. All the complete CFD results remain available within the directory structure automatically created by TURBOdesign 1.